Here we have matrix A 4 minus 1 1 2. So we need to solve x prime equal to A times x. Again, we need to find eigenvalues and eigenvectors. In this case, eigenvalues, we have repeated eigenvalues. Lambda equal to lambda 1, lambda 2. So two eigenvalues are the same, equal to 3. So we can do that. For these eigenvalues, the corresponding eigenvectors of V, we only have one linear independent eigenvectors, so we can choose V to be minus 1 1. So in this case, these eigenvalues we say defective eigenvalues. So let me just put eigenvalues lambda defective. We should have, if the matrix is diagonalizable, we should have two linear independent eigenvectors because the algebraic multiplicity is 2. But we only have one linear independent eigenvectors, so we missed one. So what we will do is to find the generalized eigenvectors. So in this case, the generalized eigenvectors, let me call this V1 to be the actual eigenvectors. V2 is a generalized one, or say V, because we have V1 later. The generalized eigenvectors is a one with choice is linearly independent from vector V, from the actual one. And the second one is satisfy this equation: A minus lambda I square V2 equal to 0. So we do know that for the eigenvalues, the actual one, is satisfy the equation A minus lambda I times V equal to 0. For the generalized one, in this case, A minus lambda I square times V2 equal to 0. So if you want to compute that explicitly, you can see that this one is actually the 0 matrix, 0, 0, 0, 0. And this is satisfied automatically because 0 matrix times any vectors will give us the vector, the 0 vector. So we only need to choose it so that V2 is independent from V. V is 1 minus 1, 1. So we choose V2 to be the simple one, 1, 0. So we have V2, the generalized one. Now we contract the chains. So we have the actual eigenvectors V1 will be, so we know that eigenvectors will always be multiple, that's V. The non-zero vectors multiple, that V, but we need V1 that determines from V2, A minus lambda I times V2, A minus lambda I. We should compute that A minus lambda I before when we compute the eigenvectors, but I skipped that part. A minus lambda I minus lambda in our case is 3, minus 3 equal 1 minus 1. A minus I times V2. V1 is this matrix times V2, which is 1, 0. This is the first column of that 1, 1. So we have the actual eigenvectors and the generalized eigenvectors. Now we construct the two linear independent equation solution. Let me call it F1t V1 E lambda t 1 1 E 3t, and the second function, the generalized one, F2t is a is V1 t plus V2 E lambda t. So one method you can remember that is you take this, you do the derivative of that. This one param will give us V1. So this is V1t. V1 is 1 1. 1 1 t, so we have t t plus V2 plus 1 0 plus 1 0 E lambda t 3t. So we get F1 and F2. The general solution is of this form. Xt is a scalar C1 times F1 plus scalar C2 times F2. So C1 V1 is lambda t plus C2 V1 t plus V2 E lambda t. This is a solution. In the general case, you see, this would be like that. In our case, it's 1 1. You just plug it in here. F1 is this, and F2 is this. This would happen in general. And for our solution, it is C1 times this plus C2 times this. So we are done with the general solution. Now we can sketch some territory. So we have two axes here correspond to x1 and x2, the two components of vectors xt, or C1 times this plus C2 times this. C1 times this plus C2 times this for the second one, x2. So let's look at the behavior when t tends to plus infinity. But let me draw the eigenvalues, eigenvectors in a generalized one. Eigenvectors V1 1 1. 1 1. It corresponds to lambda equal 3. So E 3t tend to infinity when t tend to infinity. We know that along this line is go off infinity. This is the actual eigenvectors. The generalized one is 1 0. V2. So just note V2 here. So general is when just the linear combination of something times V1 plus something times V2. Now, when t tends to infinity, maybe let's just look at this general formula. You see that t tends to infinity, this one will be so big. So because, let me put it here, xt can be written as, so we have the e lambda t in common. So e is lambda t. So this one same value. Inside we have c1 v1 plus c2 v1t plus c2 v2. So this is what xt is in general. So in the space, okay, you just put this 1 1 and 1 0 for v1 and v2. But look at that, when t tends to infinity, what happens is that this one will dominate. T tends to this one is so big, this one is just some scalars. So this is so big, is when the solution will just be dominated by v1. xt parallel to v1. So that's the first thing we see. When t is so big, it is parallel to v1. So something like this. We don't know how yet, but we know that it had to be parallel to the red one. Second one is as what happens when t is negative. When t is negative, assume that this is negative, then assume c2 is positive, for example. So this will be negative number. c2 times t, positive times negative, this is negative number. It is negative plus whatever it is, because when t is negative, infinity, for example, this is negative something. So it's negative v1 plus something v2. Negative v1 is on 1, negative of that, so it's this direction. Plus something v2. So it had to be somewhere here, right? Negative of this plus this. So it had to be something here. So we know that, okay, the curve will have some point maybe somewhere there, in this corner. So something like this. So we can check quickly at the point 1 0. What you have is matrix A, x prime equal to ax. In our case, x prime equal to ax. A is 4 minus 1 1 2 times 1 0. This one gives us 1 4 1. Vectors 4 1 is vectors 1 2 3 4 4 1, so be like that. So at this point, it's good look like this direction of the direction of 4 1. Right? So what we see is, as we said before, when t negative is somewhere there in this corner, its cross hairs go upward, and then when t is big enough, it will be parallel to this line. So the picture we can sketch is like this. Parallel to this line. Yeah. And then it will just go off infinity. And here, try to follow this a bit, and then infinity. Similarly, we can draw the other curve. That's for this. For this side, it goes like this. The other side is similar. So we know that when t is big, it is parallel to the red one. And t is equal to plus infinity, parallel to the red one. Now it would be this side, parallel to the red one. And then when t is smaller, it would go near the origin here, and then off infinity. So just kind of reflect function of this. Yeah, so these are a few of them. So this is a few trajectory of the general solution when we have the case where we have repeated eigenvalues. So in this case, we know that the origin, so from the origin we go just up infinity everywhere, right? So the origin in our case will be a source. A source is a node, so this is a nodal source. And in this case, it is improper because in this direction, opposite direction, but they have the same tangent line, the tangent to the red one. Improper nodal source. So this is the picture we would expect when we have the case repeated eigenvalues, defective eigenvalues. So we miss one eigenvectors. So we need to find the generalized eigenvectors here. We need to